My name is Talles. Good afternoon first. My name is Talles. I'm coming from Brazil to present a smart system to program body sensor networks. Pervasive monitoring demands...
Excuse me, can you be a bit more louder, please?
Okay. Sorry. It's working? No. Pervasive monitoring demands great adaptation capability of body sensor networks. In PSMs, case in which the decision made by the system is different from the decision that would be have made by healthcare professional are frequent. Assumption: the BSN has to work automatically, but has also to be always under explicit control of any clinician. I have to say that in Brazil, doctors are legally responsible for their patients' treatment, even the treatments are tailored using autonomous system. This paper introduced a deployment time programming model that could be useful for people with little grasp on programming techniques, like doctors, nurses, and the others. Deployment time programmability is a concept that refers to the definition of software artifacts and algorithms that are embedded in sensor networks, sensor nodes. This is our sensor node to capture ECG, electrocardiogram. Related works: being able to increase the transparency levels between the hardware and the programmers, but assume that the BSN user has programming language skills. Some examples: bin-watcher, abstract regions. However, these solutions do not take application domain requirement. It's important because the specialist knowledge should also be taken into consideration, as the medical expert could help in scheduling research according to each application. A smart compiler. The solution presented in this paper addressed this issue and is based on a smart intermediate level compiler. A smart compiler is capable of defining mechanisms and adjusting policies that will compose the system software image deployed into sensor nodes. Its main purpose is to increase efficiency in system usage, therefore extending the lifetime of the application. Such compilers should consider application domain requirements and hardware possibilities. Our system proposed a deployment time programming model composed of 4 activities. Activity number 1, number 2, number 3, and number 4. The main activity is performed by the agent generator, the smart system to program body sensor network. The system is composed of 3 modules. Our 4 activities: the first one, the functionality selection, refers to the descriptions of mechanisms and policies that will compose an application. This activity may be executed by any clinician through a graphical user programming interface. The second one, application requirements are sent to agent generator. The agent generator is composed of 3 modules: parser module, selector module, generator module. The first module is a parser module. It is responsible for extracting relevant information for the selector module. In practice, these informations are related to parameters such as the objective of the application, the number of tasks, the type of text, selected alarms, among the other. It's translated from the graphical user interface in a XML file. The next module is a selector module. We have a representation of the agent of the node, and the selector module will choose the best agent from this family. This is an example of the result about this model. This picture represents the implementation of the selector model, the graph representation for regular expressions, a source code. The generator module generates the file with the application source code to be compiled in the next sensor node. To do that, we have been developed an operating system called MedOS to support the agent representation. The deployment time programming model has two last stage: a compilation to the target platform. In our project, we use MESP-GCC, is a microcontroller family from Texas. And the final activity is the system initialization, which provides the monitoring signal to the healthcare professional. An important consideration: energy saving can be obtained by using dynamic power management concept, whereby the sensor node is shutting down with no interesting event occurring, or slow it down during periods of reduced activity. It's desirable that the sensor node has graceful energy quality scalability, so that if the application demands, the system is able to extend the mission lifetime at the cost of sensing accuracy. In order to allow DPM appliance in PSN, specialist knowledge needs to be taken in account. Otherwise, an efficient, graceful degradation cannot be reached, since the medical expert could help in scheduling research according to each application. Our test platform and representation of the agent that will be embedded. It's important to say that the MSP microcontroller have 5 low power modes active: LPM 0, 1, 2, and 3. For each modes, we have a current consumption, a different current consumption. In our test, we have to experiment to quantify the current consumption, have been performed to evaluate the energy consumption of some possible configuration of ECG sensor nodes, after modifying the frequency of operation and the modes. The frequency range was chosen so that this frequency would not shoot down other microcontroller pipes like AD converter and user ports. We think that the results presented reveal that there are many mechanisms that can be used for improving energy saving in BSC. When higher possibilities combined with the specialist knowledge are considered. Conclusions and future work. This work presents a proposal for paradigm shifting in BSN programming. More suitable tools such as programming interface and the smart compilers enable healthcare to work, become the actual programmer and maintainers of this technology. Future effort will be concentrated on usability tests for measuring how well the healthcare personnel can use this programming software.
Thanks very much.